Today, we're going to dive deep. I mean, really deep, into one of nature's most powerful and honestly terrifying events. We all see the headlines, we know the devastation they can cause, but what's the actual chain of events? How does a tremor miles beneath the ocean's surface transform into a colossal wall of water? Well, let's break it down, step by step. So let's just get the biggest question out of the way right from the start. We know that tsunamis are almost always triggered by underwater earthquakes. So it kind of makes sense to ask, right? Does every single earthquake that happens under the ocean kick off a tsunami? And the answer, maybe surprisingly, is a very clear no. Not even close. In fact, the vast majority of underwater quakes do absolutely nothing to the ocean surface. So, what's the deal? What makes one earthquake just a rumble in the deep, and another the terrifying start of a tsunami? Well, it turns out you need a very, very specific set of ingredients. It's kind of like a recipe for disaster, you could say. You need a perfect storm of geological conditions to all line up. If an earthquake can't tick every single one of these boxes, a major tsunami just isn't going to happen. Okay, so here's that four-part recipe based on criteria from the experts. First, and this one's pretty obvious, the location. It has to happen under the ocean. Second, it's got to have some muscle. We're talking a magnitude of at least 6.5. Third, depth. This is a huge one. The quake has to be shallow, less than about 70 kilometers deep. Any deeper and its energy just kind of fizzles out before it reaches the seafloor. And fourth, this right here is the absolute key to the whole thing. The movement has to cause vertical displacement. The seafloor has to physically move up or down. And you can see just how important that strength requirement is right here. Below a 6.5, the risk is basically zero, but look how the danger just ramps up. Between 6.5 and 7.5, you might get something, but it's rare. But then you hit that 7.6 to 7.8 range, and suddenly a destructive tsunami near the epicenter is a real possibility. And anything 7.9 or higher, well, now you're in the big leagues. You're talking about a monster event that could send devastating waves across an entire ocean basin. So we've got the conditions down, especially that all-important vertical movement. But what does that even mean? How does a huge slab of the Earth's crust suddenly lurch up or down? To understand that, we have to look at the engine that drives this entire process. And that engine almost always starts its life here, in what's called a subduction zone. This is a massive fault where two of the planet's tectonic plates are in a slow-motion collision. You've got a dense oceanic plate being forced to bend and dive underneath a lighter continental plate. This is happening right now, all around the Pacific Ocean's famous Ring of Fire. Now, you might picture this as a smooth sliding motion, but it's not. It's sticky. The edges of these plates can get locked together for decades, sometimes even centuries, but the forces pushing them don't stop. So while they're stuck, the overriding plate starts to bend into form, storing up an incredible, mind-boggling amount of energy. Think of it like you're bending a giant ruler or compressing a massive spring. And eventually, that stress just becomes too much for the rock to handle. The locked section of the fault ruptures, and in an instant, snap, all that stored energy is released. The overriding plate rebounds, it springs back upwards with incredible force. As one meteorologist put it so simply, one plate goes up and one plate goes down, it pushes the water above it up, which creates that wave. That's it. That's the moment a tsunami is born. And we are not talking about a small shift here. The scale of this movement is just colossal. During a major megathrust earthquake, like the one that devastated Japan in 2011, parts of the seafloor can be violently shoved upwards by as much as 10 meters. That's like a 3-story building suddenly jumping up from the ocean floor. You are literally lifting the entire column of water, miles deep, right along with it. So, once that huge volume of water has been lifted up, gravity immediately takes over. It collapses back down, sending waves rippling out in all directions. But here's the thing, a tsunami is not like a normal wave you see at the beach. Its journey from the deep ocean to the shore is a story of a truly wild transformation. This really shows the strange, two-faced nature of a tsunami. Out in the deep ocean, it's a speed demon. It can travel over 500 miles an hour, as fast as a commercial jet. But its wave height might only be a foot or two. A ship at sea could sail right over it and not feel a thing. But as that wave gets closer to shore and the water gets shallower, everything changes. The bottom of the wave starts dragging on the seafloor, and it slows down. All that incredible forward energy has to go somewhere, right? So it goes up. The wave gets compressed and it grows vertically, transforming from a harmless swell into a terrifying, towering wall of water. And here's something that is absolutely critical to remember. A tsunami is never just one wave. It's a whole series of them, called a wave train. And one of the most dangerous myths out there is that once the first wave hits, the danger is over. That is just not true. In fact, the first wave often isn't the biggest. More waves can show up minutes or even hours later, and the dangerous currents can stick around for a very long time. Okay, so we've got a really clear picture of how these things are born. But, knowing how it happens is one thing. Being able to predict them with better and better accuracy, that's the holy grail. And to do that, you need to get data right from the source. This is where we get into the really exciting next frontier of tsunami science. You see, for decades, the biggest hurdle for scientists has been simple access. These subduction zones are some of the deepest, most remote, and most hostile environments on the entire planet. Just think about trying to measure tiny movements in the seafloor, miles under the crushing pressure of the ocean. It's been a massive scientific and engineering headache. But now, brand new technology is completely changing the game. Check this out. Researchers working off the coast of Alaska have been using these amazing autonomous robots called wave gliders. They can stay out at sea for months at a time using super advanced satellite and sound-based tools to track the movement of sensors on the seafloor. And they can do it with centimeter-level precision. This is incredible. For the first time ever, we are literally watching the seafloor bend and buckle in near real time. And this is really just the beginning. As amazing as this new data is, scientists want to push the envelope even further. Their next big goal is to get their instruments into even deeper water, down to 3,000 or 4,000 meters. Why? Because getting measurements from that deep would put them right on top of the most critical part of the fault system, the zone where these monster tsunamis are actually generated. Which of course brings us to the ultimate question. We've figured out the recipe. We're developing the tech to watch the spring get compressed with unbelievable accuracy. But will we ever get to a point where we can predict not just that a tsunami is possible, but exactly how big it will be and when it will arrive, down to the minute? That, right there, is still the greatest challenge. If you found this deep dive interesting, and I hope you did, please do us a favor and hit that like button and subscribe to the channel. We've got plenty more explainers like this coming your way. Thanks for watching.